We're about to embark on something extraordinary. A journey that begins precisely where you are at this very moment and ends at the furthest reaches of everything we can observe. Along the way, you're going to confront a reality that might fundamentally alter your perception of existence itself. The authentic scale of the cosmos. People constantly claim the universe is enormous. This statement carries technical accuracy while being utterly insufficient. Declaring the universe is enormous resembles saying the Sahara is sandy or that the Arctic is chilly. It represents such profound understatement that it essentially becomes nonsense. The universe transcends mere enormity. It achieves vastness so extreme, so utterly beyond human comprehension, that our neural architecture never evolved the capacity to process it. Our cognitive machinery developed to calculate the distance to nearby water sources, measure the altitude of vegetation, assess the dimensions of potential threats. We never required the ability to conceive distances spanning quadrillions of kilometers. Yet tonight, that's precisely the challenge we're accepting. Before we proceed deeper, if this exploration resonates with you, hitting that like button or subscribing genuinely supports this channel's growth. Small gesture for you, massive impact for what I'm building here. Now, our voyage begins. We commence with territory you navigate effortlessly. The physical space surrounding you right now. Survey your environment. Perhaps you're situated in sleeping quarters, a common area, workspace accommodations. The boundaries probably exist somewhere between 3 and 9 meters from your position. This represents a distance your neurological processing handles without conscious effort. You estimate it visually without thinking. You've traversed similar spaces countless thousands of times throughout your existence. You possess complete intuitive understanding of what this distance represents. Consider now the entire structure containing you. Could be residential housing, multi-story dwelling, commercial complex. You navigate its layout instinctively. Movement between different areas requires zero conscious mapping. The complete footprint might extend 15 meters across, perhaps 30, potentially hundreds if you're inside substantial architecture. Still completely within manageable parameters, still firmly inside the domain of standard human experience. Mentally step beyond these walls and contemplate your immediate geographic territory, the pathways you traverse regularly, the establishments you frequent, the residences of your social connections. Perhaps your everyday realm extends several kilometers in multiple directions. This constitutes your domain, the topography that structures your daily patterns. You understand which thoroughfares experience congestion during peak hours, which alternate routes optimize travel time, where quality dining establishments exist. Everything mapped, internally, familiar terrain you navigate automatically. Your municipal area or settlement expands this territorial understanding further. Could be 16 kilometers across, perhaps 80. You might lack knowledge of every single street, but comprehension of the general configuration remains solid. The downtown core lies that direction. Residential zones spread outward this way. Major arteries cut through over there. These distances maintain human scaling. You can traverse your city in 30 minutes, perhaps 60. You've completed this journey multiple times throughout your life. Now expand your thinking to encompass your nation. If you're situated in the United States, you're considering territory roughly 4,800 kilometers coast to coast. That represents serious distance. A vehicular journey from New York to Los Angeles demands approximately 40 hours of continuous operation, assuming zero stops whatsoever. Most people executing that traverse spread it across multiple days, observing landscape transformation from Atlantic forests through Midwestern agricultural plains, through southwestern arid regions to Pacific coastal zones. It's substantial distance but conceptually graspable. Millions complete transcontinental journeys annually. It's demanding but entirely feasible. planet Earth possesses equatorial circumference of approximately 40,000 kilometers. That's 8 times the New York to Los Angeles span. If viable roadway existed following the equatorial line, circumnavigation would require roughly 560 hours of uninterrupted driving. That's nearly 24 days of constant motion. 0 breaks, 0 rest, pure perpetual movement. Realistically, Earth circumnavigation demands months when combining automotive and maritime travel, or approximately 45 hours booking continuous sequential flights globally. These constitute genuinely substantial distances, but they remain within human experiential territory. Humans have completed walking circumnavigations. Humans have accomplished sailing circumnavigations. Humans have executed aerial circumnavigations. We possess tangible understanding of Earth's dimensions because we've thoroughly explored every portion. We've mapped each landmass, charted every ocean, summited every significant peak. Earth is humanity's home, and we understand it comprehensively. But this marks the transition point. This is where numerical values start becoming strange. Because Earth, regardless of how immense it seems while standing on its surface, becomes almost impossibly minuscule compared to what exists beyond. Our first step outward brings us to something visible nearly every night. The Moon, Earth's solitary natural satellite suspended in darkness like a perpetual attendant. It appears proximate, doesn't it? During clear conditions, you can observe surface details with unaided vision. The dark regions of Luna Maria, the brilliant streaks of impact ejecta, with basic optical magnification, individual crater formations become visible. It seems almost within physical reach. But the Moon maintains approximately 384,000 kilometers separation from Earth. Let me clarify what this distance genuinely represents. If somehow you could pilot your vehicle straight upward into space maintaining highway velocities, roughly 112 kilometers per hour, reaching the Moon would consume approximately 142 days. That's approaching 5 months of continuous operation, 0 interruptions, 0 rest periods, just constant motion at velocities that trigger traffic violations on most roadways. 5 months to reach something appearing near enough to grasp. When Apollo mission astronauts travelled moonward between 1969 and 1972, they utilised the most powerful propulsion systems humanity ever constructed. The Saturn V rocket accelerated them toward velocities approaching 40,000 kilometers hourly. That's roughly 350 times faster than highway travel, and even achieving that staggering velocity, lunar arrival still required approximately 3 days. 3 days traversing empty vacuum at speeds unprecedented in human experience. Here's perspective that might assist visualization. If Earth scaled down to basketball dimensions, the Moon would approximate tennis ball size and would sit positioned roughly 7 meters distant. That's the length of a typical residential room, not adjacent to the basketball, not orbiting closely, but completely across the living space. The volume between Earth and Moon contains sufficient vastness that you could position every other solar system planet within that interval with excess capacity remaining. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune. Every single one could align between Earth and Moon with room surplus. The Moon represents the furthest destination humans have physically travelled. Among the approximately 100 billion humans who have ever existed, only 12 have walked upon another world, and that other world, the Moon, exists immediately adjacent in cosmic perspective. It's practically touching us relative to distances we're approaching. When astronauts walked lunar surfaces and communicated with mission control back on Earth, communication delay measured approximately 1.3 seconds each direction. Radio transmissions travel at light speed, the maximum possible velocity in universe structure, and even light requires over 1 second covering Earth-Moon separation. You can hear this lag in mission recordings. Every conversation contains pauses, temporal gaps, as language travels across nearly 400,000 kilometers of nothingness. Now we jump toward our solar system's centre, our star, that blazing sphere of hydrogen and helium making all terrestrial life possible. Every morning it appears, every evening it vanishes, and we rarely consider its actual distance. Our star sits approximately 150 million kilometres from Earth. This distance carries such astronomical importance, it possesses dedicated nomenclature. We call it 1 astronomical unit, or AU. It's the measurement standard we utilise for solar system distances. But before discussing that separation, let's appreciate what our star genuinely represents. It contains approximately 99.86% of all mass throughout our entire solar system. Everything else, every planet, every moon, every asteroid and comet collectively comprises less than 1/4% of solar system mass. Jupiter, the largest planet, remains massive beyond earthly comparison, yet the Sun outweighs Jupiter by roughly 1,000 times. Our star is the absolute gravitational sovereign here. Without its presence, nothing else exists. But returning to distance, 150 million kilometres. How do we conceptualise this? If you departed Earth moving toward the Sun in your vehicle maintaining highway speeds, the journey would consume approximately 192 years. That's multiple complete human lifespans. You'd begin the journey as an infant and your great-great-grandchildren wouldn't witness arrival. Light, travelling at approximately 300,000 kilometres per second, the fastest anything can possibly move through space, requires 8 minutes 20 seconds covering this distance. When you observe the Sun, you're witnessing it as it existed 8 minutes 20 seconds previously. You're observing the past. If the Sun somehow vanished at this precise instant, complete extinguishment, we wouldn't know for 8 minutes 20 seconds. We'd continue experiencing daylight, feeling warmth, living normally for over 8 minutes before darkness and cold arrived. This creates strange implications. Nothing happening on the Sun right now can affect Earth yet. There's always this 8-minute delay, this temporal buffer between solar events and terrestrial consequences. Solar flares, coronal mass ejections, any solar activity, everything requires this minimum transit time before impacting our world. Think about the Apollo missions again. Those astronauts travelled to the Moon, 384,000 kilometres away. The Sun sits 400 times further than that. 400 moon journeys. If the Apollo spacecraft had somehow pointed toward the Sun instead and maintained their velocity, reaching it would have consumed approximately 3 years of constant travel. 3 years moving through space at 25,000 miles. Hourly, that's our star's distance. That's how far away the thing making photosynthesis possible actually sits. The planets in our solar system arrange themselves at various distances from this central furnace, and each new planet we visit multiplies our distance understanding. Mercury, closest to the Sun, orbits at approximately 58 million kilometres, still closer than Earth, still within what we consider the inner solar system. Venus follows at 108 million kilometres, then Earth at 150 million. Mars orbits at approximately 228 million kilometres, about 1.5 astronomical units. This marks the boundary of the inner rocky planets. Beyond Mars lies the asteroid belt, that vast ring of rocky debris, remnants from the solar system's formation. Millions of asteroids orbit here, ranging from dust particles to bodies hundreds of kilometres across. This belt extends from roughly 300 million to 500 million kilometres from the Sun. Then come the gas giants. Jupiter, the solar system's absolute monarch among planets, orbits at 778 million kilometres, 5.2 astronomical units. This planet is colossal beyond terrestrial comprehension. You could fit over 1,300 Earths inside Jupiter. Its famous Great Red Spot, that perpetual storm system, is itself larger than our entire planet. When you observe Jupiter through a telescope, you're seeing something utterly alien. A world without solid surface, just layers upon layers of hydrogen and helium crushing down into exotic states of matter near its core. Storms larger than Earth rage for centuries. Lightning bolts thousands of times more powerful than terrestrial strikes illuminate its atmosphere. It's magnificent and terrifying simultaneously. Saturn orbits at 1.4 billion kilometers from the Sun, 9.5 astronomical units. Famous for its spectacular ring system, Saturn presents possibly the most visually stunning object in our solar system. Those rings, composed of billions of ice particles ranging from grain-sized fragments to house-sized chunks, extend hundreds of thousands of kilometers from the planet yet remain remarkably thin, sometimes only 10 meters thick. Saturn itself is another gas giant, similar in composition to Jupiter but less massive. You could fit over 700 Earths inside Saturn, yet it's so diffuse that it would actually float if you could find an ocean large enough to contain it. Its density is less than water. Think about that. A planet larger than 700 Earths that would float. Uranus sits at 2.8 billion kilometers, 19 astronomical units from the Sun. This ice giant rotates on its side, its axis tilted 98 degrees, meaning its poles point almost directly at the Sun during parts of its orbit. Nobody knows exactly why Uranus tilts this way. The leading hypothesis suggests a massive collision early in the solar system's history knocked it sideways, and it's remained that way for billions of years. Neptune, the outermost planet, orbits at 4.5 billion kilometers, 30 astronomical units from the Sun. It's another ice giant, slightly smaller than Uranus but more massive. Neptune possesses the strongest winds in the entire solar system, with some storm systems producing velocities exceeding 2,000 kilometers per hour. That's supersonic wind, storms that would tear apart anything we could engineer. When you look at Neptune through a telescope, you observe a serene blue world. But that tranquility is deceptive. Neptune is violent beyond measure. Light from the Sun takes 4 hours to reach Neptune. 4 hours travelling at the maximum possible speed through space. If you stood on Neptune's cloud tops, which you couldn't because Neptune lacks solid surface, and the atmospheric pressure would crush you instantly. But hypothetically, if you could, the Sun would appear as just another bright star. Not the disk we see from Earth, but a point of light. Brighter than other stars, certainly, but fundamentally star-like. The warmth and light that make Earth habitable barely reach Neptune. It's a cold, dark, hostile place. But we're not finished with the solar system yet. Not even close. Because beyond Neptune lies something that dwarfs all the planets combined in terms of sheer spatial extent. The Kuiper Belt begins around Neptune's orbit and extends outward to approximately 50 astronomical units. This is a vast region populated by billions of icy objects, remnants from when the solar system formed 4.6 billion years ago. Pluto orbits here, along with other dwarf planets like Eris, Makemake, and Haumea. These aren't planets in the classical sense, but they're substantial worlds nonetheless. Pluto itself, demoted from planetary status in 2006, is roughly 2,300 kilometers across. Its surface features nitrogen ice plains, water ice mountains rising 3.5 kilometers high, and a thin atmosphere that freezes and falls to the surface as Pluto moves away from the Sun in its elliptical orbit. When the New Horizons spacecraft flew past Pluto in July 2015, after 9.5 years of travel from Earth, it revealed a world far more geologically active and complex than anyone anticipated. Pluto isn't a dead frozen rock. It's a dynamic world with ongoing geological processes we still don't fully understand. But the Kuiper Belt, vast as it is, represents only the beginning of our solar system's true extent. Beyond it lies something even larger, even more distant, even more mysterious. The Oort cloud. This spherical shell of icy objects surrounds our entire solar system, extending from roughly 2,000 astronomical units to to as far as 100,000 astronomical units from the Sun. Let me help you understand what that means. The Oort cloud's outer edge sits approximately 1.5 light years from the Sun. A light year is the distance light travels in 1 year, moving at 300,000 kilometers per second. That's roughly 9.5 trillion kilometers. 1.5 light years equals about 14 trillion kilometers. The Oort cloud is so distant that objects within it barely feel the Sun's gravitational influence. They orbit so slowly that a single orbit can take millions of years. These are the most distant objects still gravitationally bound to our star, the outermost frontier of what we can legitimately call our solar system. And we've never visited it. We've never sent a probe there. We've never even directly observed most of it. We know it exists because long-period comets, those comets that take hundreds or thousands of years to orbit the Sun, originate from the Oort cloud. Gravitational perturbations from passing stars or the tidal forces of the Milky Way galaxy itself occasionally knock an Oort cloud object inward, sending it on a long plunge toward the inner solar system, where it becomes visible as a comet. The Oort cloud represents the true boundary of our solar system, and it's enormous, absolutely enormous. The distance from the Sun to Neptune, which already seemed vast at 30 astronomical units, is nothing compared to the Oort cloud. Nothing. Neptune sits 0.03% of the way to the Oort cloud's outer edge, 0.03%. Everything we think of as the solar system, all the planets, all the asteroid belt, all the Kuiper belt objects, all of it exists in a tiny bubble at the centre of the Oort cloud's vast sphere. We haven't left the solar system yet. We're still discussing our immediate cosmic neighbourhood, and already the distances have become almost incomprehensible. But now we take the biggest leap yet. Now we leave the solar system entirely and venture into interstellar space, the space between stars. The nearest star system to our Sun is Alpha Centauri, which is actually a triple star system containing 3 stars orbiting their common centre of mass. The closest component, Proxima Centauri, sits 4.24 light-years away. That's 40 trillion kilometres. Let me give you some perspective on this distance. Light, again travelling at 300,000 kilometres per second, requires 4 years and 3 months to cover this gap. 4 years at the maximum possible speed. The fastest spacecraft humanity has ever built is the Parker Solar Probe, which reached speeds of 190 kilometers per second during its close approaches to the Sun. That's fast, incredibly fast. It's the fastest human-made object in history. At that velocity, reaching Proxima Centauri would take approximately 6,600 years, 6.5 millennia. When the spacecraft launched, it was roughly 3000 BCE. The pyramids of Egypt hadn't been built yet. Writing was just being invented. Human civilization as we know it didn't exist. The spacecraft would arrive in the year 8600 CE. Everything about our current civilization, our nations, our languages, our technology, probably our species, will have changed beyond recognition. That's how far away the nearest star sits. That's the distance to our closest stellar neighbour, and space between here and there is almost perfectly empty. There's the occasional hydrogen atom, perhaps 1 per cubic centimetre on average, but mostly it's vacuum, nothing, void, darkness. If you were somehow travelling through interstellar space, you would see the Sun behind you slowly dimming, becoming just another star among many. And ahead, Proxima Centauri would gradually brighten, transforming from a faint point to a genuine sun over the course of centuries. The isolation would be absolute. No planets nearby to visit. No asteroids or comets. Just endless darkness in every direction, with only the distant stars providing any light whatsoever. This is the reality of interstellar space. This is what the universe is mostly made of. Emptiness. Our solar system, for all its size, is an island. A tiny island in an ocean of nothing, and yet stars exist everywhere. Our Milky Way galaxy contains somewhere between 200 and 400 billion stars. That's a number so large it becomes abstract. Try to visualize 400 billion of anything. You can't. The human mind simply doesn't work that way. But each one of those stars is a sun, potentially with its own family of planets, its own asteroid belts, its own comets. Each one could harbour worlds. Some of those worlds might support life, and the distances between them are uniformly vast. Interstellar space dominates our galaxy. The stars themselves occupy almost no volume. If you could shrink the Milky Way down so that the average distance between stars was 1 meter, the stars themselves would be smaller than atoms. The galaxy is almost entirely empty space with tiny points of matter scattered throughout. Our galaxy has a diameter of roughly 100,000 light-years. That means light, travelling at maximum speed, requires 100,000 years to cross from one side to the other. 100,000 years. When that light began its journey, modern humans had just begun migrating out of Africa. Neanderthals still existed. The last ice age was underway, and that light is only now reaching the opposite side of our galaxy. Think about the implications. When you look at a star on the far side of the Milky Way, you're seeing it as it was 100,000 years ago. You have no idea what that star is doing right now. It might have gone supernova 50,000 years ago, and we won't know for another 50,000 years. It might have been consumed by a black hole. It might have planets where civilizations rose and fell while the light travelled toward us. We're seeing the distant past, always the past, never the present. Our galaxy has structure. It's not a random scattering of stars, but an organised spiral with distinct features. We exist in one of the spiral arms, about 26,000 light-years from the galactic centre. The centre itself harbours something extraordinary and terrifying. A supermassive black hole called Sagittarius A star. This monster contains the mass of roughly 4 million suns compressed into a region smaller than Mercury's orbit. It's a gravitational abyss so deep that anything crossing its event horizon, the point of no return, can never escape. Not matter, not light, nothing. Black holes represent the ultimate prison, the ultimate endpoint. Once something falls in, it's gone from the universe forever, at least from our perspective. The information about what fell in might be preserved in some quantum mechanical sense on the event horizon, but that's an esoteric detail. For all practical purposes, it's annihilated. Sagittarius A star sits at the centre of our galaxy, and stars orbit it the same way planets orbit the Sun. Some of those stars maintain extremely close orbits, whipping around the black hole at incredible speeds. Astronomers have tracked individual stars completing orbits in as little as 16 years, reaching velocities approaching 3% of light speed. 3% of light speed. That's 9,000 kilometers per second. At those velocities, relativistic effects become significant. Time dilation occurs. The stars experience time differently than we do. Our galaxy rotates. The entire structure spins around its centre, and different parts rotate at different speeds. Our solar system orbits the galactic centre at approximately 220 kilometers per second. That sounds fast, and it is. But the galaxy is so vast that completing one orbit takes approximately 225 million years. We call this period a galactic year. Since Earth formed 4.5 billion years ago, our solar system has completed roughly 20 galactic orbits, 20 trips around the Milky Way. When we last occupied this position in the galaxy, dinosaurs ruled Earth. The last time before that, the continents were configured differently. Pangaea hadn't formed yet. The time before that, complex life had just begun to emerge from the oceans. Each galactic orbit witnesses profound changes on Earth, yet the galaxy itself remains largely unchanged. The Milky Way doesn't exist in isolation. It's part of a small galaxy group called the Local Group, which contains roughly 80 galaxies. Most are dwarf galaxies, small collections of a few billion stars. But the Local Group also includes Andromeda, the nearest large spiral galaxy to the Milky Way. Andromeda sits approximately 2.5 million light-years away. That distance deserves its own contemplation. 2.5 million light-years. Light from Andromeda takes 2.5 million years to reach us. When you observe Andromeda on a dark night, and you can see it with unaided eyes as a faint smudge in the constellation Andromeda, you're seeing it as it existed 2.5 million years ago. At that moment in Earth's history, the genus Homo had just emerged. Our earliest ancestors were learning to use stone tools. Everything that defines human civilization, agriculture, writing, cities, nations, technology, all of it lay in the unimaginable future. And the light showing us Andromeda was already travelling through space toward Earth. Andromeda is larger than the Milky Way. It contains roughly 1 trillion stars, more than twice our galaxy's population. It's a magnificent spiral, similar in structure to our own galaxy, but grander in scale, and it's approaching us. The Milky Way and Andromeda are gravitationally attracted to each other, and they're falling together at roughly 110 kilometers per second. In approximately 4 billion years, they will collide. I should clarify what galactic collision means. The galaxies won't smash into each other like solid objects. Remember, galaxies are mostly empty space. The stars are so far apart that when two galaxies merge, almost no stars actually collide with each other. Instead, they pass through each other's spaces, and gravity does the real work. The gravitational interactions will distort both galaxies, stretching them, twisting them, ultimately merging them into a single larger galaxy. Astronomers have dubbed this future galaxy Milkomeda. Our solar system will likely survive this merger intact, though our position in the galaxy will change. We might be flung into the outer halo, or we might end up closer to the new galactic centre. The night sky will transform completely. Stars will crowd much closer together from Earth's perspective. The merged galaxy will look nothing like what we see now. But this collision lies 4 billion years in the future. Our Sun will have exhausted its hydrogen fuel and begun expanding into a red giant by then, likely consuming Mercury, Venus, and possibly Earth. The Sun's transformation represents a far more immediate threat to Earth than galactic collision. Still, the fact that we can predict galactic collision billions of years in advance demonstrates how well we understand cosmic mechanics. We can model the gravitational interactions between objects containing hundreds of billions of stars and predict their evolution over timeframes that dwarf all of human history. The local group, containing the Milky Way Andromeda and their smaller companions, exists as part of a larger structure called the Virgo supercluster. This is a massive collection of galaxy groups and clusters spanning roughly 110 million light-years. The Virgo supercluster contains at least 100 galaxy groups and clusters, totaling approximately 47,000 galaxies. Each of those galaxies contains billions or trillions of stars. Each of those stars potentially hosts planets. The numbers become so large they lose meaning. How many planets exist in the Virgo supercluster? Trillions upon trillions, perhaps quadrillions. We can't count them. We can only estimate based on what we've observed nearby and extrapolate outward. And the Virgo supercluster is just one supercluster among millions. The universe contains structure at every scale. Planets orbit stars. Stars cluster into galaxies. Galaxies group together. Galaxy groups form clusters. Clusters combine into superclusters. And superclusters arrange themselves along filaments and sheets, surrounding vast cosmic voids. This larger scale structure, the cosmic web, extends across billions of light-years. The filaments composed of dark matter and ordinary matter contain the superclusters. The voids, regions containing very few galaxies, occupy most of the universe's volume. If you could somehow view the universe from far enough away to see this structure, it would resemble a sponge or a neural network. Dense regions connected by filaments with empty spaces between. This structure arose from tiny quantum fluctuations in the very early universe, fluctuations that got amplified by cosmic inflation and then shaped by gravity over billions of years. We're seeing the ghost of quantum mechanics written across the largest structures in existence. But we still haven't reached the edge. We still haven't encountered the limits of observation. The observable universe extends far beyond the Virgo supercluster, far beyond even the cosmic web structures we can map. The most distant objects we can observe exist approximately 46 billion light-years away in all directions. That creates a sphere around us centered on Earth, with a radius of 46 billion light-years. This is the observable universe, and it contains everything we can possibly see. Wait, you might notice something strange about that number. If the universe is approximately 13.8 billion years old, and light has been travelling toward us since the beginning, shouldn't the most distant objects be 13.8 billion light-years away? The answer involves the expansion of space itself. The universe is expanding. Space itself is stretching, carrying galaxies away from each other. The most distant light we can see left its source approximately 13.8 billion years ago, shortly after the Big Bang. But during the time that light has been travelling toward us, the space between us and that source has been expanding. The source has been moving away from us the entire time. So now, 13.8 billion years later, that source exists not 13.8 billion light-years away, but 46 billion light-years away. The light shows us where the object was 13.8 billion years ago. But the object itself is much farther now. This expansion isn't objects moving through space. It's space itself expanding, carrying everything with it. Imagine dots on a balloon. As you inflate the balloon, the dots move apart, but they're not moving across the balloon's surface. The surface itself is stretching. That's analogous to cosmic expansion. Though the universe isn't expanding into anything, there's no outside. Space itself is what's expanding. This expansion has profound implications. The most distant galaxies are receding from us faster than light speed. Not because they're moving through space faster than light, which remains impossible, but because the space between us and them is expanding faster than light can cross it. This creates a cosmic horizon. Light from objects beyond a certain distance will never reach us, because the space between us and them is expanding too quickly. That light keeps travelling toward us, but it makes no progress because space is stretching faster than the light can cross it. It's like running on a treadmill that's accelerating faster than you can run. You're moving forward, but you're actually losing ground. This horizon divides the universe into two regions. The observable universe, containing everything we can possibly see, and the unobservable universe, containing everything we cannot and will never see. Both regions contain galaxies, stars, planets, perhaps life. But we're forever separated from the unobservable universe. No information from there can ever reach us. No light, no gravity waves, no signals of any kind. It's not just far away, it's fundamentally inaccessible. How large is the unobservable universe? We don't know. It could be just slightly larger than what we can see. It could be infinite. Current measurements suggest it's at least 250 times larger than the observable universe, but that's a minimum estimate. It could be vastly larger still. Some cosmological models suggest the universe extends infinitely in all directions, meaning the unobservable universe is literally infinite. Other models propose finite but unbounded geometry, similar to the surface of a sphere but in higher dimensions. We simply lack the data to distinguish between these possibilities. What we observe suggests the universe is flat or very nearly flat, which is consistent with either infinite extent or a very large finite size well beyond what we can observe. This creates a strange situation. We exist in a universe where most of reality is forever hidden from us. The observable universe, as vast as it is, might represent only a tiny fraction of what exists. We're like someone in a room with opaque walls, able to see only what's inside the room, unable to determine what lies beyond or even if there is a beyond. The cosmic horizon imposed by expansion means we can never escape this limitation. We can never see beyond a certain distance, and that distance, perversely, is shrinking in terms of what we'll be able to observe in the future. Because the universe's expansion is accelerating. This acceleration, driven by something we call dark energy, means that distant galaxies are receding from us ever faster. Galaxies currently visible will eventually recede beyond the cosmic horizon and disappear from view. In the far future, trillions of years from now, hypothetical observers will see a vastly emptier sky than we do. The local group of galaxies will have merged into a single large galaxy, but beyond that, space will appear essentially empty. All other galaxies will have receded beyond the cosmic horizon, their light unable to reach observers because space is expanding too quickly. Those future observers might conclude they live in a universe containing only a single galaxy, surrounded by infinite empty space. They would be wrong, but they'd have no way to discover their error. The evidence would be gone. We're fortunate to exist at a time when the universe's history is still readable in the sky. We can see distant galaxies. We can observe the cosmic microwave background, that faint glow of radiation from the Big Bang that fills all space. We can reconstruct cosmic history because the evidence still exists, but that evidence is slowly vanishing, carried away by cosmic expansion. This realization carries philosophical weight. We exist at a special time in cosmic history, a window when the universe can be understood. Too early, and the universe would be too hot and dense for complex structures like galaxies and stars and planets. Too late, and the evidence of cosmic history would have receded beyond the horizon. We inhabit a narrow temporal window where conscious observers can exist and can actually understand the cosmos they inhabit. Is that coincidence? Perhaps. Or perhaps it's selection bias. We can only observe the universe at times when observers can exist, so naturally we find ourselves in this window. It's similar to asking why we find ourselves on a planet suitable for life. The answer is obvious. Observers must exist in places where life can survive, so we shouldn't be surprised to find ourselves in such a place. The same logic applies to time. Nevertheless, it creates a sense of cosmic fortune. We exist when the universe can be comprehended. We exist after it's become structured enough to support complex chemistry and life, but before it's expanded so much that its history becomes invisible. This moment, cosmically speaking, won't last forever. I want to give you one more journey, not outward through space this time, but backward through time. Because the light reaching us from distant objects isn't just showing us faraway places, it's showing us the past. When you look at the moon, you're seeing it as it was 1.3 seconds ago. When you observe the sun, you're seeing it 8 minutes in the past. Proxima Centauri appears as it was 4 years ago. Andromeda shows itself as it existed 2.5 million years ago. The most distant galaxies we can observe appear as they were over 13 billion years ago, when the universe was young. Look at your hand right now. The light from your hand reaches your eyes almost instantaneously. The tiny travel time is immeasurably short. You're seeing your hand as it exists in the present, or close enough that the distinction is meaningless. Now look at the moon. That light left the moon's surface 1.3 seconds ago. You're seeing the moon's past. Not the distant past, but genuinely the past nonetheless. If the moon exploded right now, you wouldn't know for 1.3 seconds. Look at the sun. 8 minutes and 20 seconds in the past. If it vanished, Earth would continue in its orbit for 8 minutes and 20 seconds before we'd notice anything wrong. Look at the night sky. Every star you can see with your eyes exists in our galaxy, the Milky Way. The closest are a few light years away. The most distant naked eye stars are several thousand light years distant. You're seeing them as they were years or millennia ago. Some might have already exhausted their fuel and collapsed. Some might have gone supernova, blasting their outer layers into space, but their light hasn't reached us yet, so we still see them shining peacefully. With a telescope, you can see much further. Andromeda becomes visible, showing you a galaxy as it was 2.5 million years ago. More powerful telescopes reveal galaxies billions of light years away, galaxies that existed when the universe was young, galaxies that might look completely different now or might not exist anymore at all. The most distant object ever observed is a galaxy whose light has been travelling for over 13.4 billion years. We're seeing it as it existed just 400 million years after the Big Bang. At that time, the universe was a vastly different place, much smaller, much denser, much hotter. The first stars had only recently ignited. Galaxies were just beginning to coalesce from the hydrogen and helium created in the Big Bang. This distant galaxy appears small and irregular, lacking the grand spiral structure of mature galaxies like the Milky Way or Andromeda. It's a primitive galaxy, one of the first. We're witnessing cosmic dawn, the birth of structure in the universe, and we're seeing it billions of years after it happened. That galaxy, as it exists now, is invisible to us. It's too far away. The light showing us its current state won't reach Earth for billions of years yet. By the time that light arrives, Earth will likely no longer exist. The sun will have expanded into a red giant, possibly consuming our planet entirely. The receivers capable of detecting that ancient light will be gone. This is the nature of cosmic observation. We always see the past. The present state of distant objects is unknowable. We can predict what they might be doing based on our understanding of physics, but we can't observe them directly. The universe enforces a strict information limit. Nothing can travel faster than light. Information about distant events can only reach us at light speed. For nearby objects, this delay is trivial. For distant ones, it becomes profound. The edge of the observable universe represents the ultimate information boundary. Beyond it lies regions of space whose current state we can never know, whose very existence we can never verify, whose properties we can never measure. They might as well not exist as far as we're concerned, and yet they probably do exist. The same physics that operates here presumably operates there. Similar galaxies probably fill that space. Similar stars probably shine, perhaps similar planets orbit those stars. Perhaps life evolved on some of those worlds. Perhaps civilizations arose, but we'll never know. They're forever beyond our reach, forever isolated by the expansion of space itself. This isolation defines existence at cosmic scales. Every civilization that might exist out there beyond our horizon faces the same limitation. They can never reach us. We can never reach them. The universe's structure guarantees eternal separation between sufficiently distant regions. No matter how advanced a civilization becomes, no matter what technology they develop, they cannot overcome the expansion of space itself. You cannot travel faster than light. That's a fundamental law of physics, not an engineering challenge. And even if you could somehow achieve light speed, which you can't, you still couldn't reach regions beyond the cosmic horizon, because space expands faster than light can cross it. This means the universe contains countless unreachable islands of existence, each one isolated from all the others by the relentless expansion of space. We exist in one such island. Our observable universe is our prison and our kingdom simultaneously. Everything within it is theoretically accessible, at least in principle, though the practical challenges remain staggering. Everything beyond it is forever denied to us. Consider what this means for the search for extraterrestrial intelligence. Scientists have been listening for radio signals from alien civilizations for decades. We've found nothing. Silence. Some interpret this as evidence that we're alone, but the cosmic horizon provides another explanation. Even if civilizations exist out there broadcasting powerful signals in all directions, we can only detect those civilizations within our observable universe. And within that sphere, we can only detect signals from civilizations that exist right now, accounting for a light travel time. A civilization that existed 10 billion years ago and broadcast for millions of years before going extinct. we'd never hear from them. The signals already passed Earth long before humanity evolved. A civilization that will arise in a distant galaxy 10 billion years from now, we'll never hear from them either. Their signals won't reach Earth until long after our sun has died. We can only detect the tiny subset of civilizations that happen to exist at the right time and the right distance to have their signals reaching Earth during the brief window when humans are listening. When you frame it that way, the silence becomes less surprising. We're searching for a very specific needle in an incomprehensibly vast haystack, and we've barely begun looking. The universe might teem with life, might host millions of civilizations, and we'd still hear nothing because of the constraints imposed by distance and time. This brings us to a profound realization about our cosmic situation. We are isolated, profoundly, perhaps permanently isolated. Earth sits in a remote spiral arm of the Milky Way, a galaxy that itself occupies no special position in the universe. We're not at the centre, we're not in a dense region. We're in a fairly typical location, which means most of the universe is far away from us. The nearest potentially habitable planet we know of orbits Proxima Centauri, 4.2 light-years distant. If humans ever travel there, and that's a monumental if, the journey will take thousands of years with any currently conceivable technology. Communication with any colony established there would involve years of signal delay. You couldn't have a conversation. You could exchange messages, but each response would arrive years after you sent your question. Building an interstellar civilization faces challenges that dwarf anything in human history. And that's just to reach the nearest star. Genuine galactic civilization, spanning thousands of light years, becomes almost inconceivable. Information would take millennia to cross such distances. No central authority could govern. No shared culture could exist except in the most abstract sense. Each star system would be effectively independent, connected to others only through messages arriving from the distant past. Some science fiction imagines faster than light travel solving these problems. Warp drives, hyperspace, wormholes, various fictional technologies that let you cheat the light speed limit. But these ideas contradict known physics. They require exotic matter with negative mass or energy, things we've never observed and have no reason to believe exist. They might be genuinely impossible, not just technologically difficult, but fundamentally prohibited by the structure of reality. If that's true, and current physics suggests it is, then the isolation is permanent. The light speed limit isn't a temporary obstacle, it's an eternal constraint. Civilizations can never meaningfully interact across cosmic distances. They're doomed to develop alone, unaware of each other, separated by gulfs of space and time that technology cannot bridge. This isolation carries both sadness and wonder. Sadness because it means we might truly be alone in any practical sense, even if life exists elsewhere. We'll never meet them, never learn from them, never share knowledge or art or philosophy. Each civilization faces existence alone. But wonder too, because it means the universe is larger and stranger than we can fully grasp. Out beyond our horizon, beyond the reach of our telescopes and instruments, reality continues. Galaxies form and evolve, stars ignite and die. Planets orbit in systems we'll never observe. Perhaps life emerges, evolves, builds civilizations. Perhaps those civilizations ask the same questions we ask, wonder if they're alone, search the skies for signals they'll never receive. The universe is vast enough to contain infinite variety, infinite possibility, and we'll never know most of it. Let's return to the question of scale one more time. Let's put some of these distances in perspective using comparisons that might make them slightly more comprehensible. If the Sun were the size of a basketball, roughly 30 centimeters in diameter, Earth would be a tiny ball bearing about 3 millimeters across, sitting 26 meters away. That's roughly the length of a tennis court. You could fit this model in a large park. The Moon would be less than 1 millimeter across, about 7 centimeters from Earth. Barely noticeable at the scale we're working with. Mars would be another ball bearing, slightly larger than Earth, sitting 40 metres from the basketball sun. Jupiter would be a baseball, 30 centimetres in diameter like the Sun itself, positioned 140 metres away. That's farther than you can throw a baseball, even though Jupiter is represented by a baseball in this model. Saturn would be slightly smaller, 250 metres distant. Neptune, the outermost planet, would be another baseball sitting 800 metres from the Sun. That's half a mile. You'd need to walk 10 minutes at a normal pace to get from the Sun to Neptune in this model. Now where would the Oort cloud be? Its outer edge would sit roughly 20 kilometres away. 20 kilometres. If your basketball sun sat in the centre of the city, the Oort cloud would extend beyond the city limits into the surrounding suburbs. And we still haven't left the solar system. Where would Proxima Centauri be in this model? 7,000 kilometres away. If your basketball sun sat in New York City, Proxima Centauri would be approximately in India. You could fly there on an airplane, but you'd need hours to make the trip. And remember, this is the nearest star. Most stars in our galaxy would be much, much farther away in this model. The Milky Way's diameter would be roughly 180 million kilometres at this scale. The nearest large galaxy, Andromeda, would sit about 4.5 billion kilometres away. The edge of the observable universe would be roughly 3 trillion kilometres distant at this scale. These numbers still don't mean much, do they? They're too large. The compressions don't help because even compressed, the distances overwhelm intuition. Let's try another approach. Let's compress even further. Imagine the entire solar system out to the Oort cloud, reduced to the size of a US quarter coin, 24 millimeters across. Everything we've discussed, all the planets, all the moons, all the asteroids and comets, the Kuiper belt, the Oort cloud, all of it fits in a space smaller than a quarter. At this scale, the Sun itself would be invisible, far too small to see even with a microscope. Earth would be smaller than an atom. The planets wouldn't exist at any scale you could observe. They'd be quantum fluctuations, effectively nothing. Now, at this scale, where would Proxima Centauri be? About 4 meters away. Another quarter-sized disk, 4 meters distant. The Milky Way would be a disk roughly 670,000 kilometers across, large enough to fit 2 moons placed side by side. Andromeda would be a similar disk 14 million kilometers away. The observable universe would be a sphere roughly 2.7 billion kilometers in radius. Still enormous. Still beyond easy comprehension. Even compressed to the point where solar systems become smaller than coins, the universe remains vast. Here's perhaps the most striking way to understand cosmic scale. Consider time instead of space. Light travels very fast, 300,000 kilometers per second. Nothing moves faster. Light can circle Earth's equator 7.5 times in 1 second. That's genuinely fast. In 1 second, light travels farther than most people travel in a day, yet light from the nearest star takes over 4 years to reach us. From Andromeda, 2.5 million years. From the edge of the observable universe, 13.8 billion years. Time provides a natural measure of cosmic distance, because the universe's expansion means looking farther away always means looking further back in time. Every photograph of a distant galaxy is a photograph of the ancient past. The deeper we look into space, the earlier we see into cosmic history. The most distant galaxies appear to us as they were when the universe was young, just forming its first structures. We cannot see these galaxies as they exist now. Their current state is unknowable. The light showing us their present won't reach Earth for billions of years, long after our sun has died. This temporal aspect of cosmic observation creates strange implications. When you look at the night sky, you're seeing a mixture of different times. Close stars appear as they were years ago, distant stars as they were centuries or millennia ago, nearby galaxies as they were millions of years ago, distant galaxies as they were billions of years ago. The night sky is a collage of different eras, all presented simultaneously to your eyes. There's no universal now, no cosmic present moment shared by all locations in space. Different regions of space exist at different moments in their own timelines, and we observe them at different points in their histories depending on how far away they are. Relativity makes this even stranger. Time itself flows at different rates depending on velocity and gravity. An observer moving very fast relative to you experiences time more slowly than you do. An observer deep in a gravitational field experiences time more slowly than someone far from massive objects. These aren't illusions or measurement errors. Time genuinely flows at different rates in different circumstances. If you spent years travelling near light speed and then returned to Earth, you'd find that less time had passed for you than for people who remained on Earth. You'd have aged less. This has been experimentally verified countless times. Atomic clocks flown on, airplanes run slower than identical clocks left on the ground, exactly as relativity predicts. GPS satellites must account for relativistic time dilation, or their positioning would be off by kilometres. This is established physics, not speculation. Now imagine trying to coordinate events across cosmic distances with relativistic effects and light speed delays both operating. An event happens on a planet orbiting a star 10 light years away. When did it happen from Earth's perspective? When we observe it 10 years after it occurred? When it actually occurred in the planet's reference frame? There's no single answer. Different reference frames assign different times to the same event. The universe doesn't have a universal clock. Time is local, relative, dependent on motion and gravity. This makes cosmic coordination impossible in any absolute sense. You can't point at the Andromeda galaxy and say what's happening there right now, because right now has no meaning across 2.5 million light years. You can say what you're observing right now, which shows Andromeda as it was 2.5 million years ago. You can predict what might be happening there in your reference frame based on physics and evolution, but you cannot know the present state. These deep features of reality, the light speed limit, the expansion of space, the relativity of time, all conspire to isolate different regions of the universe from each other, not just practically but fundamentally. The universe's structure enforces separation. Let me share something that might help you grasp just how empty space really is. Consider the distances between objects relative to their sizes. Earth has a diameter of roughly 12,700 kilometres. The Moon, approximately 384,000 kilometres away, is therefore about 30 Earth diameters distant. That's not so far relative to size. You could line up 30 Earths between Earth and Moon. But the Sun sits 12,000 times Earth diameter away. 12,000 Earth diameters. That's starting to be a significant gap. Neptune sits 35 million Earth diameters from the Sun. The Oort cloud extends to 1.2 billion Earth diameters. Proxima Centauri sits 300 billion Earth diameters away. 300 billion. If you lined up Earths touching each other between here and Proxima Centauri, you'd need 300 billion of them. That's more Earths than stars in our galaxy. The Milky Way's diameter equals roughly 7 quadrillion Earth diameters. The observable universe spans roughly 7 sextillion Earth diameters. A sextillion is 1 followed by 21 zeros. These numbers are absurd, meaningless. No human brain can actually process them. We can write them down, calculate with them, but we cannot truly comprehend them, and that's the point. The universe is fundamentally incomprehensible at the level of direct human intuition. We can understand it mathematically, model it, predict its behaviour, but we cannot feel it the way we feel the room around us. Our brains didn't evolve for this. Let's shift perspective again. Instead of distances, consider number of objects. The observable universe contains approximately 2 trillion galaxies. Each galaxy contains anywhere from a few million to several trillion stars. Let's be conservative and say the average galaxy contains 100 billion stars. That means the observable universe contains roughly 200 billion trillion stars. That's 2 followed by 23 zeros, 200,000 billion stars. Each of those stars potentially hosts planets. Recent observations suggest most stars have at least one planet. Many have several. If we conservatively estimate 2 planets per star on average, that's 400 billion trillion planets in the observable universe. Some of those planets orbit in their star's habitable zone, the region where liquid water can exist on the surface. Maybe 1 in 10 stars has a habitable zone planet. That's still 40 billion trillion potentially habitable worlds. 40 billion trillion places where life might exist. Does life exist on any of them besides Earth? We don't know. We found no evidence of life beyond Earth despite decades of searching. But we've barely begun to look. We've examined a tiny handful of nearby stars in detail. We've studied exactly 1 planet thoroughly enough to confirm life exists there, and that's the planet we're standing on. The absence of evidence isn't evidence of absence, especially when you've examined such a minuscule sample. Perhaps life is rare. Perhaps the conditions required for life to arise are so specific, so unlikely, that Earth is the only living world in the observable universe. That seems improbable given the numbers involved, but it's possible. Perhaps we're genuinely alone. Perhaps consciousness emerged exactly once in all of cosmic history, here, on this world, in the brains of primates who evolved to survive in African grasslands. If that's true, it's both terrifying and profound. It means consciousness is precious beyond measure, a unique phenomenon that must be protected because it exists nowhere else. It means when you die, a portion of the universe's total consciousness vanishes permanently. It means humanity carries the entire burden of cosmic awareness. We're the only eyes through which the universe observes itself. Or perhaps life is common. Perhaps it arises wherever conditions permit. Perhaps millions of worlds in our galaxy alone host living organisms. Perhaps thousands host intelligent civilizations. Perhaps we're surrounded by life, by consciousness, by other minds asking the same questions we ask. But we can't see them because of the distances involved, because of the cosmic isolation enforced by light speed and expansion. Perhaps we're all alone together, each civilization trapped in its own bubble of observability, unaware of the others, unable to communicate across the vast gulf separating us. We don't know which scenario is true. We might never know. The universe might keep this secret forever, teasing us with possibilities we cannot verify. Both scenarios carry weight. Both inspire awe and humility. Whether we're alone or surrounded by life, the cosmos remains magnificent, terrible in its vastness, beautiful in its complexity. Here's something that might surprise you. Despite all this vastness, despite the incomprehensible distances and the billions of galaxies and the trillions of stars, most of the universe is not matter. Most of it is something else entirely. Ordinary matter, the atoms that make up stars and planets and you and everything you can see, comprises only about 5% of the universe's total mass energy. 5%. Everything we can observe directly, every star, every galaxy, every cloud of interstellar gas, all of it combined makes up 1/20th of what exists. So what's the other 95%? We call it dark matter and dark energy, but those names don't explain what they are. They're placeholders, labels. But we don't know what dark matter is. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation at all as far as we can tell. It only interacts through gravity. It might be exotic particles that only rarely interact with ordinary matter. It might be something stranger still. Experiments around the world are trying to detect dark matter directly, but so far all searches have come up empty. We can map its distribution by observing its gravitational effects. We can see where it clusters, but we cannot capture it, cannot study its properties, cannot determine what it fundamentally is. Then there's dark energy. This comprises roughly 68% of the universe's mass energy. It's even more mysterious than dark matter. Dark energy appears to be a property of space itself, a fundamental energy density that exists everywhere, even in empty vacuum, and it's causing the universe's expansion to accelerate. Distant galaxies aren't just moving away from us, they're moving away faster and faster as time passes. This acceleration defies normal gravity. which should slow expansion. Something is pushing space apart, working against gravity, driving cosmic acceleration. We call that something dark energy. But we don't understand it. We don't know what causes it. We don't know why it has the strength it does. We can measure its effects precisely, but explaining those effects remains one of the biggest unsolved problems in physics. Think about what this means. 95% of the universe consists of things we don't understand, things we can barely detect, things we certainly cannot explain. We've built sophisticated theories describing how atoms work, how stars burn, how galaxies form. We can trace cosmic evolution back to fractions of a second after the Big Bang. We can predict the behaviour of black holes and neutron stars, but we don't know what most of the universe is made of. Our comprehension of reality is limited to the 5% that emits or absorbs light. The other 95% remains mysterious. This should inspire humility. We've learned an enormous amount about the cosmos. Our understanding has progressed dramatically over the past century, but vast territories of ignorance remain. Fundamental questions about reality's nature lack answers. We exist in a universe we can describe mathematically but cannot fully understand. Perhaps future discoveries will illuminate dark matter and dark energy. Perhaps we'll develop new physics that explains these phenomena. Or perhaps they'll remain mysterious, aspects of reality forever beyond our ability to comprehend. The scale of the cosmos forces us to confront our own insignificance. Earth is a tiny world orbiting an ordinary star in an unremarkable galaxy. Everything humans have ever done, every war fought, every empire built, every work of art created, every scientific discovery made, all of it happened on this speck of cosmic dust drifting through the void. The entirety of recorded history, roughly 5,000 years, is nothing compared to cosmic timescales. The universe is 13.8 billion years old. Human civilization has existed for less than 1/1,000,000th of 1% of cosmic history. If you compressed the age of the universe into a single year, with the Big Bang occurring on January 1st at midnight, humans wouldn't appear until the last minute of December 31st. Recorded history would occupy the final second. Your individual lifetime wouldn't register. It would be immeasurably brief, a flickering instant lost in the vastness of cosmic time. Yet here we are, conscious, aware, capable of understanding our own cosmic insignificance. That's remarkable. The universe evolved for billions of years, and eventually in at least one location, it produced structures complex enough to become self-aware. Matter arranged itself into patterns capable of contemplating their own existence. Atoms formed in ancient stars, scattered across space by supernovae, eventually coalesced into planets, and on at least one planet, those atoms organised into living cells, and those cells evolved into organisms capable of building telescopes and studying the cosmos that created them. You are a way for the universe to know itself. That's not poetic exaggeration, it's literal truth. The atoms in your body were forged in stellar furnaces billions of years ago. You're made of star stuff, and you can understand that fact. You can trace your atomic ancestry back to ancient supernovae. You can comprehend the processes that created the elements in your bones and blood. That's extraordinary. Consciousness might be rare in the universe, or it might be common. We don't know, but its existence at all seems unlikely. The laws of physics didn't need to permit complexity. The universe could have remained simple, just hydrogen and helium expanding forever, never forming structures. But the laws are what they are, and they allow complexity. They allow atoms to bond into molecules, molecules into cells, cells into organisms, organisms into ecosystems, ecosystems into planetary biospheres containing billions of species. And somewhere in that cascade of increasing complexity, consciousness emerged. Brains developed that could not only process information but experience it subjectively. The universe became aware of itself from the inside. What is that awareness worth in a cosmos this vast? Is human consciousness meaningful when set against the scale of galaxies and the age of the universe? One perspective says no, we're irrelevant, cosmically insignificant. The universe doesn't care about us. It will continue its expansion long after our sun has died and Earth has been destroyed. The laws of physics operate without regard for human concerns. Our existence or non-existence makes no difference to cosmic evolution. But another perspective says yes, consciousness is meaningful precisely because it's rare and fragile. Perhaps we're the only aware beings in the observable universe. Perhaps consciousness exists in only one location, here, on this world. If that's true, then we represent something unique. The universe has been evolving for nearly 14 billion years. For most of that time, it consisted of unconscious matter and energy, following physical laws without awareness. Then consciousness emerged. The universe woke up. It began experiencing itself. It started asking questions about its own nature. That transformation from unconscious to conscious might be the most significant event in cosmic history. More important than the formation of the first stars. More important than the creation of the heavy elements. More important than the evolution of galaxies. Because consciousness changes everything. It introduces meaning into a universe that previously had none. An unconscious universe just is. It exists. It evolves according to physical law. But there's no meaning in that existence, no purpose, no value. Nothing matters in an unconscious cosmos because there's no one for it to matter to. Consciousness changes that. Meaning requires a mind to comprehend it. Purpose requires an agent to pursue it. Value requires someone to value. Consciousness provides these things. It introduces subjectivity into an otherwise objective reality, and perhaps we're the only consciousness. Perhaps Earth hosts the only minds in the universe. If so, we carry an enormous responsibility. We're the custodians of meaning itself. If we destroy ourselves, we extinguish not just human civilization, but potentially the only consciousness that exists. The universe would return to its previous state, vast and magnificent but utterly meaningless, because there would be no one to appreciate it. This raises profound ethical questions. Do we have a duty to preserve consciousness? Do we have an obligation to spread it beyond Earth, to ensure that some disaster on our planet doesn't extinguish awareness from the cosmos? Should we prioritize the survival of intelligence above other values? These aren't easy questions, and I don't pretend to have answers, but they're worth contemplating. Our cosmic context matters. Understanding our place in the universe should inform how we think about our responsibilities and our future. Let's return to scale one more time, but from a different angle. Consider the cosmic calendar, that thought experiment where the entire history of the universe gets compressed into a single year. The Big Bang happens at midnight on January 1st. For months, nothing much happens. Space expands, particles form, radiation fills the universe. Eventually, the first stars ignite. Galaxies begin to form. The early months of the cosmic calendar feature universe-wide processes, things happening on the largest scales. Our Milky Way galaxy doesn't form until late May. Think about that. For nearly half the universe's history, our galaxy didn't exist. The Sun and Earth don't appear until September. Life on Earth doesn't emerge until late September. For most of the cosmic year, Earth is lifeless. Just rock and water and atmosphere, sterile and empty. The first multicellular organisms don't appear until late November. Complex life is very recent on the cosmic timescale. Dinosaurs? They show up on December 25th. They dominate Earth for several days on this compressed timescale, then go extinct on December 30th. Humans? We don't appear until late on December 31st. Modern humans emerge around 11:58 p.m. Agriculture gets invented around 11:59 and 30 seconds p.m. Everything recognizable as human civilization, all our cities and technologies and accumulated knowledge, exists in the last 30 seconds of the cosmic year. You were born in the last fraction of a second. Your entire life, everyone you've ever known, everything you've ever experienced, all compressed into a duration shorter than a heartbeat on the cosmic timescale. This perspective is simultaneously humbling and liberating. Humbling because it emphasizes how recent and brief we are. The universe existed for nearly 14 billion years without us. It will continue for trillions more after we're gone. Our moment is fleeting, but liberating too because it frees us from cosmic significance we never possessed. The universe doesn't revolve around humanity. We're not the center, not the purpose, not the culmination of anything. We're a recent development on one planet, and that's fine. It means we can stop pretending we're special in any cosmic sense, and instead focus on what actually matters, the experiences and relationships and projects that give our lives meaning on human scales. We don't need to be cosmically significant to matter. We matter to each other. We matter in the context of our own lives. That's enough. The universe's indifference doesn't diminish the value of human love, human creativity, human curiosity. These things matter because we experience them, because they shape our lives, because they create the texture of conscious existence. Cosmic scale provides context, not judgment. It shows us where we fit in the larger picture, and the picture is staggeringly large, far beyond anything our ancestors could have imagined. Ancient peoples looked at the same stars we see, but they couldn't know what those stars were. They invented mythologies, imagined gods and heroes written across the heavens. They didn't know those points of light were distant suns. They couldn't conceive of the distances involved. For most of human history, the universe seemed small. The Earth was the center. The sun and moon orbited around us. The stars were perhaps lights attached to a celestial sphere, rotating daily around our world. This geocentric model made sense based on what people could observe. The ground beneath your feet seems stationary. The sky appears to revolve overhead. Without sophisticated instruments, without mathematical models, the Earth-centered universe seems obvious. It took enormous intellectual courage to challenge that model. Copernicus proposed that Earth orbits the Sun, not the reverse. This heliocentric model explained planetary motions more elegantly, but it violated common sense and religious doctrine. Earth wasn't the center of everything. We were just another planet. Galileo supported the heliocentric model with telescopic observations. He saw moons orbiting Jupiter, demonstrating that not everything circles Earth. He observed phases of Venus, proving it orbits the Sun. The evidence mounted. The universe refused to conform to human assumptions. Earth lost its central position, but the revolution didn't stop there. For a while, people imagined the solar system was the universe. The Sun and its planets were all that existed. The stars were distant, sure, but perhaps not that distant. Perhaps they were small, dim objects scattered nearby. Then measurements of stellar parallax proved stars were vastly more distant than anyone had imagined, light years away, and the Milky Way, that band of light across the sky, was revealed to be a disk of billions of stars. Our sun was just one star among multitudes. The universe expanded in human understanding, but perhaps the Milky Way was the entire universe. Perhaps all those stars represented the full extent of reality. This seemed reasonable for a time. Then came another revolution. Those fuzzy nebulae visible through telescopes, were they clouds within our galaxy, or separate galaxies entirely? Edwin Hubble settled the question in the 1920s. He measured the distance to the Andromeda Nebula and found it was far beyond the Milky Way's boundaries. It was another galaxy, comparable in size to ours, containing billions of stars. And if Andromeda was a separate galaxy, then all those other spiral and elliptical nebulae might be galaxies too. The universe expanded again. Suddenly it contained billions of galaxies, each with billions of stars. And then Hubble made another discovery. The distant galaxies were receding from us. Their light showed redshift, indicating motion away from us. And the more distant the galaxy, the faster it receded. Space itself was expanding, carrying galaxies apart. This led to the Big Bang theory. If galaxies are moving apart, then in the past they must have been closer together. Trace back far enough, and everything must have been compressed into an incredibly dense, hot state. The universe had a beginning. Not an eternal past, but a moment of origin roughly 14 billion years ago. Everything we observe emerged from that initial expansion. With each discovery, the universe revealed itself as larger, older, stranger than anyone expected. And we're still making discoveries. We're still revising our understanding. The journey from geocentric Earth to observable universe spanning 93 billion light years represents one of humanity's greatest intellectual achievements. We expanded our perspective from our immediate surroundings to cosmic scales, using mathematics and observation to map a reality far beyond direct human experience. This expansion of understanding continues. Every generation learns more. Future discoveries might reveal realities we currently cannot imagine. Perhaps the observable universe is just one bubble in a vast multiverse. Perhaps our physical laws are local, and other regions operate under different rules. Perhaps dimensions exist beyond the three of space, and one of time we experience. We don't know. But history suggests our current understanding, as sophisticated as it is, remains incomplete. The cosmos probably harbours mysteries we haven't begun to suspect. That's both exciting and humbling. Exciting because there's always more to discover, always deeper understanding to pursue. Humbling because it reminds us that despite our progress, vast ignorance remains. Now, as we near the end of this journey, let me bring us back to where we started. You, sitting wherever you are, existing in this present moment. You're composed of atoms formed in ancient stars. You're connected through an unbroken chain of causation to the Big Bang itself. Every particle in your body has a history spanning billions of years. You're part of the cosmos, literally made of the same material as stars and planets. And you're aware of this fact. You can understand your own cosmic context. That understanding doesn't change your day-to-day life in obvious ways. You still need to eat, sleep, work, maintain relationships. The bills still need paying. The daily challenges still exist. But it provides perspective. It contextualizes human existence within something much larger. When you look up at the night sky, you're not just seeing pretty lights. You're seeing deep time. You're seeing vast distances. You're seeing the universe as it was, not as it is. You're connected to all of it through the laws of physics that govern everything from quarks to galaxy clusters. The same gravity that keeps you on Earth's surface also holds galaxies together. The same electromagnetic force that allows chemical bonds in your body also powers stars. The same quantum mechanics that creates uncertainty at subatomic scales also explains why atoms don't collapse. You're subject to all these forces. You're a product of these laws. You exist because the universe permits complexity, because physics allows atoms to form molecules, to form cells, to form organisms, and somehow, improbably, wonderfully, you're conscious. You can think about these things. You can appreciate the cosmos. You can feel awe at its vastness. That capacity for awe, for wonder, for curiosity, might be one of consciousness's most valuable features. It drives us to explore, to question, to seek understanding beyond immediate survival needs. We don't just react to our environment. We try to comprehend it. We build models. We test hypotheses. We accumulate knowledge across generations. And gradually, slowly, we've assembled a picture of cosmic reality that would astonish our ancestors. We've measured the universe. We've traced its history. We've mapped its structure. We've identified its components, even those we don't yet understand. This represents an incredible achievement for a species that evolved to survive on African grasslands. We've transcended our evolutionary origins. We've developed tools, mathematics, experimental methods that extend our senses and reasoning far beyond their natural limits. We've achieved understanding that our brains weren't designed for, and we're still progressing. Future humans, if they exist, will know more than we do. They'll have better instruments, more sophisticated theories, deeper understanding. They might look back on our knowledge the way we look back on ancient cosmologies, appreciating the effort but recognizing the limitations. Or perhaps we're approaching limits. Perhaps there are questions we cannot answer, realities we cannot access, mysteries forever beyond reach. Perhaps the unobservable universe, dark matter, dark energy, these will remain mysterious. Perhaps consciousness itself defies complete explanation. We don't know. But the search continues. The quest for understanding drives forward. And even if ultimate answers remain elusive, the journey itself has value. The act of questioning, of exploring, of building knowledge, this creates meaning in human life. We're not just existing, we're trying to understand existence. We're participating in the universe's self-awareness. So where does this leave us? We started this journey in your room and travelled outward through ever-increasing scales of distance and time. We passed the moon, our star, the planets, left the solar system behind, crossed interstellar space, traversed our galaxy, reached distant galaxies, approached the cosmic horizon itself. At each step, the numbers grew larger, more difficult to comprehend. At each scale, we confronted the limits of human intuition, and throughout this journey, one theme repeated: vastness, emptiness, distance beyond measure. The universe is mostly empty space, punctuated by occasional concentrations of matter. And even those concentrations, the galaxies and stars and planets, are themselves mostly empty. Atoms are tiny nuclei, surrounded by vast clouds of electron probability. The nucleus itself, though it contains almost all the atom's mass, occupies only 1/1,000,000,000th of the atom's volume. Everything you think of as solid is actually nearly empty. Your body, this chair you're sitting on, the ground beneath your feet, all of it is mostly vacuum with occasional particles scattered through it. Scale down to atoms, and the emptiness becomes apparent. Scale up to cosmic distances, and the emptiness dominates even more. Stars separated by light years, galaxies separated by millions of light years, galaxy clusters separated by hundreds of millions of light years. The universe is structure embedded in emptiness. And we exist in this universe, these tiny conscious patterns of matter, trying to understand the whole while being an infinitesimal part of it. The endeavour seems absurd when you think about it. Beings whose lives span decades trying to comprehend a cosmos spanning billions of years and billions of light years, creatures bound to a single planet attempting to understand the entire observable universe. And yet, we've made progress. We've learned things. We've built knowledge. We've measured cosmic distances and traced cosmic history. We've identified the forces governing reality and mapped their effects across space and time. We've taken our limited senses and limited cognition and extended them through instruments and mathematics until they could grasp, however imperfectly, the nature of the cosmos itself. That achievement deserves recognition. We should feel proud of what humanity has accomplished. We've gone from geocentric ignorance to cosmic understanding in just a few centuries. We've revealed reality's structure through patience, creativity, and systematic inquiry. And there's more to discover. Always more questions to ask, more observations to make, more understanding to build. The universe won't reveal all its secrets easily, but it will reveal them to those who look carefully enough. So when you finish listening to this, when you return to your daily life with all its mundane concerns, remember occasionally to look up. Remember that those points of light in the night sky are distant suns. Remember that you're seeing ancient photons that travelled for years or centuries or millennia to reach your eyes. Remember that you exist in a universe almost incomprehensibly vast, yet you can comprehend it. You're made of atoms forged in stars. You're subject to the same physical laws that govern galaxies. You're part of this cosmos, not separate from it. And for reasons we don't fully understand, you're aware. You can contemplate your own existence and the existence of everything around you. That's remarkable. That's precious. Whatever challenges you face, whatever concerns occupy your thoughts, you're participating in something extraordinary. Your consciousness emerging from matter, you're the universe becoming aware of itself. And on this small world, during this brief cosmic moment, you have the privilege of knowing that. Good night. Before we truly conclude, let me offer you some specific reference points that might help anchor what we've discussed. Not to memorize, but to carry with you as mental landmarks when contemplating cosmic scale. The moon sits 384,000 kilometers away. Light crosses that distance in 1.3 seconds. That's the farthest any human has travelled in person. Only 24 individuals have made that journey, and only 12 actually walked on the lunar surface. Everyone else who has ever lived remained bound to Earth, our sun. That fusion furnace providing all the energy that powers life on Earth maintains a distance of 150 million kilometres. 8 minutes 20 seconds of light travel time. If something catastrophic happened to the sun right now, we'd continue our normal activities for over 8 minutes before the consequences arrived. Neptune, the most distant planet in our solar system, orbits at 4.5 billion kilometres from the sun. Light requires 4 hours to span that gap. The Oort cloud, that vast spherical shell of icy objects marking our solar system's true boundary, extends to roughly 14 trillion kilometres, 1.5 light years. Objects there orbit so slowly that a single revolution requires millions of years. Proxima Centauri, our nearest stellar neighbour, resides 4.2 light years distant, approximately 40 trillion kilometres. With current technology, reaching it would require thousands of years. The centre of our Milky Way galaxy lies 26,000 light years away, about 250 quadrillion kilometres. The supermassive black hole there, Sagittarius A star, contains 4 million solar masses compressed into a region smaller than Mercury's orbit. Andromeda, our nearest large galactic neighbour, exists 2.5 million light years distant. The light you see from Andromeda tonight began its journey toward Earth when our ancestors were just learning to craft stone tools. Modern humans didn't exist yet. The Virgo supercluster, the largest structure containing our local group of galaxies, spans 110 million light years. It contains approximately 47,000 galaxies, each potentially hosting billions of stars and trillions of planets. The observable universe extends 46 billion light years in all directions, creating a sphere 93 billion light years across centered on Earth. This sphere contains approximately 2 trillion galaxies. Each galaxy averages perhaps 100 billion stars. That's 200 billion trillion stars total. An incomprehensible number. Most of those stars likely host planets. The universe is 13.8 billion years old. It began in an incredibly hot, dense state and has been expanding and cooling ever since. For the first 380,000 years, it was too hot for atoms to form. Electrons couldn't bind to nuclei. The universe was opaque, filled with plasma. Then it cooled enough for atoms to form. Electrons combined with protons and helium nuclei. Light could suddenly travel freely. The universe became transparent. That moment of transition, called recombination, is what we observe as the cosmic microwave background radiation. It's the oldest light in the universe, the afterglow of the Big Bang itself, now stretched by cosmic expansion into microwave wavelengths. The first stars formed roughly 100 million years after the Big Bang. These were massive, short-lived objects composed only of hydrogen and helium, the elements created in the Big Bang. No heavier elements existed yet. When these first stars exhausted their fuel and exploded as supernovae, they scattered newly forged heavy elements into space. Carbon, oxygen, nitrogen, iron, all the elements necessary for planets and life, were created in stellar cores and supernova explosions. Every atom in your body heavier than hydrogen was manufactured inside a star. You're genuinely, literally made of stardust. This isn't poetic language, it's direct physical fact. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of it was synthesized in stellar furnaces billions of years ago. Our solar system formed 4.6 billion years ago from a cloud of gas and dust enriched by previous generations of stars. That cloud collapsed under its own gravity, forming the sun at the center and a disk of material around it. Within that disk, dust grains stuck together, forming larger clumps. Those clumps collided and merged, building progressively larger objects. Eventually, planets emerged from this process of accretion. Earth formed from countless collisions between smaller bodies. Early in its history, probably within the first 100 million years, a Mars-sized object struck the proto-Earth in a catastrophic impact. The collision vaporized rock, melted the surface, and ejected enormous amounts of material into orbit. That orbiting debris eventually coalesced into the Moon, so the Moon is literally a piece of Earth, torn away by violence and reformed in orbit. Life appeared on Earth surprisingly quickly after the planet cooled enough to support it. The earliest evidence for life dates back at least 3.8 billion years, possibly earlier. Within a billion years of Earth's formation, living organisms already existed. For most of Earth's history, life remained microbial. Single-celled organisms dominated for over 3 billion years. They transformed the planet, particularly by producing oxygen through photosynthesis. The oxygen they generated accumulated in the atmosphere, eventually reaching levels that could support more complex life forms. Multicellular organisms emerged roughly 600 million years ago. Complex animals with specialized tissues and organs appeared during the Cambrian explosion, a relatively brief period when most major animal body plans evolved. The history of complex life on Earth spans only about 15% of the planet's total age. Humans represent an even tinier fraction. The genus Homo emerged roughly 2.5 million years ago. Anatomically modern humans, Homo sapiens, appeared roughly 300,000 years ago. Behavioral modernity, including sophisticated language, art and technology, developed within the last 100,000 years. Agriculture was invented around 12,000 years ago, enabling permanent settlements and eventually cities. Writing appeared roughly 5,000 years ago, marking the beginning of recorded history. Everything before that is prehistory, accessible only through archaeology and genetic evidence. Industrial civilization, with its factories and fossil fuels and global communication networks, is less than 300 years old. The internet, which has transformed human society in fundamental ways, became publicly available only 3 decades ago. In cosmic terms, in geological terms, even in biological terms, human civilization is extraordinarily recent. We've existed for a brief moment, and yet in that moment we've achieved understanding that spans cosmic scales. We've measured distances to galaxies billions of light years away. We've detected gravitational waves from colliding black holes. We've discovered thousands of planets orbiting other stars. We've mapped the cosmic microwave background and confirmed the Big Bang theory. We've identified dark matter and dark energy through their effects on galaxies and cosmic expansion. We've built particle accelerators that recreate conditions from microseconds after the Big Bang. We've developed quantum mechanics and general relativity, theories that describe reality at the smallest and largest scales. This represents remarkable progress. A species that evolved to hunt and gather on African savannas has developed mathematics sophisticated enough to model black holes and predict cosmic evolution. We've transcended our evolutionary constraints through culture and technology, but we remain vulnerable. Earth is our only home. If something catastrophic happens here, human civilization ends. We have no backup, no colony on another world, no way to evacuate significant numbers of people if disaster strikes. This fragility creates urgency around certain questions. Should we prioritize spreading beyond Earth? Should we establish permanent settlements on other worlds to ensure humanity's survival? Or should we focus on protecting Earth, solving the problems here before attempting to expand elsewhere? These aren't easy questions. Space colonization faces enormous technical challenges. Mars, the most frequently cited target, is hostile to life. Its atmosphere is too thin to breathe, offering no protection from radiation. Its surface is cold and dry. Water exists, but as ice or in trace amounts. Growing food would require enclosed habitats. Every resource would need to be carefully managed. And Mars is the easy target. It's relatively close, reachable in months with current technology. It has some atmosphere, some water, some useful resources. Everywhere else in the solar system is worse. Venus is too hot, its atmospheric pressure too extreme. The outer planets are gas giants lacking solid surfaces. Their moons might be habitable with significant technological intervention, but they're far away and bathed in radiation. Interstellar colonization faces even greater obstacles. The distances are so vast, the journey time so long, that any such mission would span multiple human generations. The travellers who departed would die en route. Their descendants would arrive. Creating a viable closed-loop ecosystem for such a journey remains beyond current capabilities. We don't know how to build ships that could sustain human life for centuries. Perhaps future technology will solve these problems. Perhaps we'll develop fusion propulsion, or some other advanced system that reduces travel times. Perhaps we'll learn to create perfect life support systems. Perhaps we'll genetically modify humans to better survive hostile environments. Or perhaps we'll remain bound to Earth permanently. Perhaps the universe's structure genuinely prohibits expansion. Perhaps the distances are too vast, the challenges too severe, the resources required too enormous. We don't know yet, but the scale of the universe suggests that even if we do spread beyond Earth, we'll remain confined to our immediate cosmic neighbourhood. The Milky Way might become accessible over thousands or millions of years, but other galaxies will remain forever out of reach. The light speed limit enforces this. Space's expansion reinforces it. We live in a universe where most of reality is inaccessible, where cosmic horizons limit what we can ever know or reach. This might seem depressing, but I find it oddly comforting. It means the universe retains mystery. No matter how much we learn, vast unknowns remain. No matter how far we travel, if we travel at all, endless distances stretch beyond our reach. The cosmos is inexhaustible. There's always more to wonder about. Now, I want to address something you might be feeling after this journey through cosmic scales: insignificance, perhaps even nihilism. If we're so small, if the universe is so vast, if our entire species occupies only a brief moment in cosmic time, what's the point? Why does anything matter? This question has troubled people for as long as they've understood cosmic scale, and there's no universally satisfying answer. Different philosophical traditions offer different responses, but let me share one perspective that resonates with me. Meaning isn't something the universe provides. The universe doesn't have intentions. It doesn't assign purpose. It simply exists, following physical laws, evolving according to those laws without any goal or aim. Meaning is something consciousness creates. You create meaning through your choices, your values, your relationships, your projects. The universe's vastness doesn't diminish that meaning. It just contextualizes it. Your life matters because you experience it, because others experience their relationships with you, because your actions have consequences in the lives of people around you. That mattering operates on human scales. It doesn't need cosmic validation. Consider love. When you love someone, does that love become less real or less valuable because the universe is vast? Of course not. The love exists in the relationship between conscious beings. Its reality and value are entirely contained within that context. The fact that Andromeda Galaxy exists 2.5 million light-years away has no bearing on whether your love is meaningful. Consider creativity. When someone creates art or music or literature, does the artistic value decrease because stars are dying in distant galaxies? No. The value exists in the experience of creation, and the experiences of those who encounter the art. Cosmic scale is irrelevant to artistic meaning. Consider knowledge. When we discover something new about nature, when we solve a problem or develop understanding, does that achievement become worthless because the observable universe contains 2 trillion galaxies? No. The knowledge has value because conscious beings can use it, can appreciate it, can build upon it. Human scale meaning exists independently of cosmic scale. The universe's vastness provides context. It shows us we're not the center of everything. It demonstrates that reality extends far beyond human concerns, but it doesn't negate human meaning. It just shows that meaning is local, created by conscious beings, operating on scales where consciousness exists. And consciousness might be rare, we don't know, but it's possible that Earth hosts the only aware beings in the observable universe. If so, we're extraordinarily precious. We're where the universe has become capable of understanding itself. That's profound. That's significant regardless of cosmic scale. Even if consciousness is common, even if millions of civilizations exist throughout the galaxy, each one creates its own meaning. Each one matters in its own context. The existence of others doesn't diminish any individual civilization's value. So when confronted with cosmic scale, with the vast emptiness between stars, with the billions of galaxies and the trillions of stars, don't conclude that nothing matters. Instead, recognize that mattering happens at the scale where consciousness operates. Recognize that you participate in creating meaning through your awareness and your choices. Recognize that being small in the cosmos doesn't make you insignificant in your own life or the lives of those around you. The universe is vast and ancient and mostly empty. And within that vastness, on this small world, consciousness emerged. You emerged. You're aware of the cosmos that created you. You can contemplate your place within it. You can feel awe at its scale and beauty. That capacity for awe, that ability to understand and appreciate reality, might be the most remarkable thing the universe has produced. Atoms arrange themselves into patterns capable of comprehending atoms. Matter became capable of understanding matter. The universe generated observers who can observe it. This seems miraculous, even though it's natural. It required no supernatural intervention, just physics operating over billions of years. But the outcome, consciousness aware of its cosmic context, remains extraordinary. You're part of that extraordinary outcome. Your existence represents billions of years of cosmic evolution. Your awareness represents the universe knowing itself. Your experiences, your thoughts, your relationships, your creative acts, all of this is the universe doing things it couldn't do when it was just unconscious matter and energy. So yes, you're small. Yes, the universe is vast. Yes, cosmic scale dwarfs human scale. But none of that diminishes what you are or what you can do. Your consciousness in a mostly unconscious cosmos. Your awareness in a vast ocean of unaware matter. Your meaning-making in a universe that generates no inherent meaning. That's remarkable. That's valuable. That's worth celebrating. As we close this exploration, I hope you carry forward not just knowledge about cosmic distances and timescales, but also a sense of perspective. Perspective about humanity's place in the universe. Perspective about your own life in relation to cosmic scale. Perspective about what matters and why. The room you're sitting in right now exists on Earth, a planet orbiting an ordinary star in an unremarkable galaxy. That galaxy is one among trillions. The observable universe extends billions of light years in all directions. Most of it will remain forever beyond human reach, forever unknown to human science. And yet here you are, aware of all this, capable of contemplating it, capable of appreciating the beauty and vastness and mystery of it all. When you step outside tonight or tomorrow night, look up if the sky's clear. Find a dark location away from city lights if possible. Let your eyes adapt to the darkness and observe. Those points of light are distant suns, that faint band stretching across the sky, if you can see it, is our galaxy viewed from within. That fuzzy patch in Andromeda constellation, if you can spot it, is an entire galaxy of 1 trillion stars. You're seeing ancient light, photons that travelled for years or millennia or millions of years to reach your retina. You're connected to all of it through physics, through chemistry, through the fundamental laws that govern reality, from the smallest quantum scales to the largest cosmic structures. And you can understand that connection. You can comprehend your place in the cosmos. You can appreciate the journey those photons made to reach you. That understanding, that capacity for appreciation, makes you extraordinary regardless of how small you might seem against cosmic scales. Thank you for taking this journey with me. Thank you for engaging with these ideas, for contemplating cosmic scale, for expanding your perspective beyond everyday concerns to consider the full scope of reality. The universe is vast and beautiful and mysterious, and you're part of it. You're made of star stuff. You're conscious matter contemplating unconscious matter. You're the universe observing itself. Never forget how remarkable that is. Sweet dreams, and may the cosmos fill your mind with wonder rather than dread. Good night. Let me share one final reflection on what we've explored together tonight. We began this journey with familiar scales, distances you navigate daily, spaces your brain handles effortlessly. Your room, your neighbourhood, your city. These are the scales evolution prepared you for. Your ancestors needed to understand how far to the next water source, how high that tree stands, how much distance separates them from potential threats. Natural selection optimized your spatial cognition for these everyday distances. Then we expanded outward, step by step, each new distance multiplying what came before. The moon, 384,000 kilometers, seemed impossibly distant until we compared it to the sun at 150 million kilometers. The sun seemed far until we considered Neptune at 4.5 billion kilometers. Neptune seemed remote until we encountered the Oort cloud extending trillions of kilometers. Each scale dwarfed the previous one, and yet we kept going. The Oort cloud, vast as it is, occupies only a tiny fraction of the distance to Proxima Centauri. Proxima Centauri sits practically on our doorstep compared to the galactic centre. The galactic centre is nearby compared to Andromeda. Andromeda is close compared to distant galaxy clusters, and all of it, every distance we discussed, every measurement we contemplated exists within the observable universe. Beyond our cosmic horizon lie regions we cannot observe, perhaps cannot ever observe, regions that might extend infinitely, or might curve back on themselves in ways we cannot visualize. The scale compounds, it multiplies, it overwhelms, and that's precisely the point. The universe is incomprehensible in its totality. You cannot hold it all in your mind simultaneously. You can understand pieces, you can grasp individual concepts, you can follow the logic connecting different scales, but the whole, the complete picture, the full scope of cosmic reality that exceeds human cognitive capacity. We evolved for different purposes. Our brains were not designed to comprehend light years and billions of years. They were designed to recognize faces, track animals, plan hunts, maintain social relationships. The fact that we can understand cosmic scales at all represents a triumph of human cognition extended through culture and technology. Mathematics provides the tools our natural intuition lacks. We can calculate distances we cannot feel. We can model timescales we cannot experience. We can reason about realities far beyond immediate perception. This mathematical ability, combined with systematic observation and experimental verification, has allowed us to map the cosmos despite our cognitive limitations. But there's a cost to this understanding. Once you know cosmic scale, you cannot unknow it. Once you've contemplated the distances between stars, the emptiness of space, the vast age of the universe, these facts become part of your worldview. They change how you see everything. Some people find this liberating. The cosmic perspective frees them from petty concerns. If the universe is so vast, if our lives are so brief, Why worry about minor embarrassments or temporary setbacks? Nothing we do matters cosmically, so we're free to create our own meaning without cosmic judgment. Other people find it oppressive. The cosmic perspective makes them feel insignificant, purposeless, adrift in an uncaring universe. If nothing matters cosmically, why does anything matter at all? Why strive? Why create? Why care? Both responses are understandable. Both reflect genuine engagement with cosmic scale. There's no objectively correct reaction. How you integrate cosmic perspective into your life remains a personal choice. But I'll offer this suggestion. Use cosmic scale to calibrate your concerns, not to eliminate them. When something troubles you, ask whether it will matter in a year, in a decade, in a century. Most daily frustrations fail even the one-year test. They're temporary, fixable, ultimately trivial. Letting them dominate your emotional state gives them importance they don't deserve. But some things do matter beyond brief timescales. Relationships, if nurtured, can last lifetimes. Knowledge, once created, can persist across generations. Actions you take today can have consequences decades from now. These things matter on human scales, and human scales are the scales where you actually live. You don't exist in cosmic time. You exist in human time measured in heartbeats and breaths and days and years. You don't inhabit cosmic space. You inhabit human space, measured in rooms and cities and the occasional flight across continents. Cosmic scale provides context, but human scale provides content. The texture of your life, the experiences that make existence meaningful, these happen at human scales. A conversation with a friend happens across meters, lasting minutes or hours. Reading a book happens in a chair, occupying hours or days. Creating something, whether art or music or writing or code, happens at human scales. Learning a skill takes months or years. Raising children takes decades. Building a career spans decades. These are the timescales and distances where life actually occurs. Cosmic perspective shouldn't diminish their importance. It should highlight their preciousness. You have a limited time in this universe. Decades, if you're fortunate. A century, if you're very fortunate. That's infinitesimal cosmically, but substantial personally. What you do with that time, how you spend those years, these choices shape your existence and the existence of those around you. The universe won't remember. Cosmic evolution won't care. But you'll experience it. The people you interact with will experience it. That experience, that conscious awareness of life as it unfolds, that's where value exists. Don't waste your limited time on things that don't matter to you. Don't let cosmic scale paralyze you into inaction or nihilism. Use it instead as a filter. Filter out the trivial. Focus on what actually enriches your experience and the experiences of others. Be kind, because kindness creates positive experience in a universe that doesn't mandate positivity. Be curious, because curiosity leads to understanding and appreciation. Be creative, because creation adds complexity and beauty to reality. Be compassionate, because consciousness is rare and precious, and alleviating suffering in other conscious beings matters even if the cosmos doesn't care. These aren't cosmic imperatives. The universe doesn't command you to be kind or curious or creative or compassionate. These are choices conscious beings can make, choices that shape experience in positive ways, and experience is all we have. Your internal life, your subjective awareness, that's your window into reality. Make it a window worth looking through. Fill it with wonder rather than dread. Fill it with curiosity rather than cynicism. Fill it with connection rather than isolation. The cosmos provides the stage. Vast, ancient, mostly empty, beautiful in its structure, terrible in its scale, but you provide the story. You decide what matters. You create meaning through your choices and actions. That agency, that creative capacity, makes you significant even in an insignificant cosmos. Now, truly at the end of this journey, I want leave you with one image. Picture yourself standing on Earth's surface at night. Above you, the stars shine, ancient light from distant suns. Below you, the ground is solid, made of minerals formed in the planet's violent early history. Around you, air flows, oxygen produced by billions of years of photosynthetic life. Inside you, atoms cycle through metabolic processes, the same atoms that once existed in stars, in nebulae, in the early universe itself. You're not separate from the cosmos. You're cosmos observing cosmos. You're a localized pattern of complexity in a universe that permits complexity. Your awareness emerging from atoms that individually possess no awareness. You're extraordinary in a universe where most things are ordinary. Hold that image. Remember it when you need perspective. Remember that you're part of something vast and ancient and ongoing. Remember that your awareness of this fact makes you special even if your size and lifespan are cosmically insignificant. The journey we've taken tonight from your room to the edge of the observable universe reflects humanity's journey from ignorance to understanding. Our ancestors knew only their immediate surroundings. They couldn't conceive of continents, much less planets, much less galaxies. We've expanded human knowledge across cosmic scales in just a few centuries of systematic science. That expansion continues. Future generations will know more than we do. They'll see further, understand deeper, perhaps even travel to destinations we can only observe. They'll build on what we've learned, extending human understanding even further. You participate in this ongoing project. Every time you learn something new about the cosmos, every time you engage with scientific understanding, you're connecting yourself to humanity's expanding knowledge. You're part of the species that went from geocentric mythology to cosmic cartography in a few thousand years. That's remarkable. That's worth celebrating. And it's still unfolding. We haven't reached the limits of understanding. We've barely begun. So much remains unknown. So many mysteries await solution. The universe continues to challenge us, continues to reveal deeper layers of complexity and beauty. As you return to your daily life, as you navigate familiar spaces and familiar concerns, carry this cosmic perspective with you lightly. Don't let it crush you. Don't let it diminish what matters to you. Instead, let it enhance your appreciation. Let it make the ordinary seem more precious because it's so rare. Life is rare. Consciousness is rare. Understanding is rare. You possess all three. That makes you extraordinary even if the cosmos is indifferent. The universe is vast beyond comprehension. When you comprehend that vastness, that paradox, that tension between your smallness and your awareness of your smallness, that's what makes human existence profound. We're tiny and temporary and located in an unremarkable corner of an unremarkable galaxy. And we know it. We can measure our own insignificance. We can contemplate our own briefness. That self-awareness transforms everything. Thank you for sharing this journey through cosmic scales. Thank you for engaging with these ideas even when they challenge intuition and exceed imagination. Thank you for being curious about reality beyond immediate experience. The universe is lucky to have observers like you, conscious beings capable of appreciating its vast and terrible beauty, and you're lucky to exist in a universe comprehensible enough to reward curiosity with understanding. Sleep well, dream of stars and galaxies and the vast dark spaces between them, and wake tomorrow, knowing you're made of the same matter as all of it, connected through physics and chemistry and the long history of cosmic evolution. Your stardust contemplating stars, never forget how remarkable that is. Good night.